And our final bit of algebra techniques that I want to remind you of is the idea of a surd. So we call a number that is the square root of a, we call that a surd. And the thing is, unless a turns out to be a perfect square like, sorry, get it on. So unless a turns out to be a number like 1, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, etc., unless it's one of those, this number here, where if you were to try and write it as a decimal, its decimal approximation would go on forever with no repeats. So in other words, you can't write down very easily the exact value of these things, and so we tend to leave it just as the square root of 17. That's the exact value. As soon as you try to write down a decimal, you only get an approximate value. And so as a result, it becomes important that we actually can work with surds. And it turns out, here are the properties of these numbers. Here are the properties of surds that we need. And it says, obviously, if you've got the square root and you square it, you get the number itself. Or if you've got the square and you take the square root, you get the number itself. That much we know. It also turns out that the square root of a times b is the square root of a times the square root of b, and so on. Okay, so these are properties of these numbers, and we can use these in rearranging algebraic expressions. And this last one is just the distributive law again. Only this time the number that's common is the square root of a. So the distributive law is super important. So, let's have examples of using each of these laws. A says the square root of 3 times the square root of 5, using law 2 backwards. This is the same as the square root of 3 times 5. And so I can say the square root of 3 times the square root of 5 is the square root of 15. Which one of those is simpler? Who knows? They're just the same number. All right, so I've rearranged them in there. Part B. Says, I've got the square root of 5 times 2 times the square root of 5. Now we know that the square root times the square root just gives the number itself. So that just gives me 5 times 2, and so I get 10. See? The square root, now this one actually has a pronumeral in it, but according to law 3, I can write that as the square root of 9 times x squared over the square root of 4. The square root of 9 times x squared I can write as the square root of 9 times the square root of x squared, all over. Now the square root of 4 is just 2. The square root of 9 is 3, the square root of x squared is x, and so that simplifies to 3x on 2. D, 6 on the square root of 3. At that stage, that's fairly simple, but I can rearrange this I can do what's called, I can rationalise the denominator. I can turn the denominator into a number that's not a surd by multiplying both the numerator and the denominator by the square root of 3. So I'm multiplied by 1. Now, in the numerator, I end up with 6 times the square root of 3. In the denominator, I have the square root of 3 times the square root of 3, which by law 1 is just 3. And now I've got 6 divided by 3, so that ends up being 2 root 3. So 6 on the square root of 3 is the same number as 2 times the square root of 3. And lastly, part E, I have 4 root 3 plus 2 root 3 minus 1 root 3. So I've got 4 of these numbers, plus 2 gives me 6, minus 1 is 5, so that just becomes 5 root 3. And in there I've actually used law 4. But just add them up. Whatever that number is, if I've got 4 of them, I add another 2 of them, I've got 6 of them. Take away 1, I've got 5 of them. Whatever that number is, 5 root 3. Now, we can sometimes simplify surds if I can factorise the number into some number times a perfect square. So the numbers that we had here before, 1, 4, 9, 16, 25, etc. And probably the easiest way to, that's sitting there, but it's easier if I show you with a number. So let me go here with A. The square root of 18, I'm looking for, has it got a factor of 1, 4, well obviously it's got a factor of 1, but has it got a factor of 4, 9, 16, 25? Well clearly 9 goes into 18. So I can write that as 2 times 9. Now using my laws of surds, that's the square root of 2 times the square root of 9. And since this is a perfect square, the square root of 9 is 3, so I can write that as 3 root 2. So I can say the square root of 18 is the same as 3 root 2. And we tend to say 3 root 2 is simpler than square root of 18. So we tend to say that's simpler. Likewise, the square root of 75. Again, I'm looking, does 4 go into 75? No, it doesn't. Does 9 go into 75? No. 16? No. But 25 does. So in here, this is the square root of 3 times 25, which becomes the square root of 3 times the square root of 25, and so that becomes 5 root 3. So using this idea, we can start to simplify these things here. So let me just go through and do these. The square root of 7 times the square root of 27. Well, I can't do anything with the square root of 7, but in here I can say the square root of 27 is the square root of 3 times 9. So that's the square root. So that's the square root of 7 times, in here, 3 root 3. And now I'm going to say 7 times 3 is 21, so that's going to be 3 times the square root of 21. Square root of 7 times the square root of 3 is the square root of 21. You could have, if you like, multiplied 7 by 27 and then tried to simplify that, but I think it's easier if you can do the simplifications first. It's certainly easier on your mental arithmetic, let me tell you that. So let's go again. Square root of 8 times the square root of 12. Now the square root of 8 I know is 2 times, or 8 is 2 times 4. 12 is 3 times 4, and you can see 4 is good because it's one of my perfect squares. And so this will become 2 root 2 times 2 root 3. The square root of 4 is 2, the square root of 4 is 2. Now 2 times 2 is 4, and 2 times 3 is 6, so I end up with 4 root 6. Root 2 plus 2 root 3 minus root 2 plus root 3. So in this case they're pluses, so I can't do much there, but I've got 3 root 2 minus 1 root 2, so that will be 2 root 2. And here I've got 2 root 3 plus a root 3, so that will be plus 3 root 3. And given that that's a plus in there, I can't do anything else. That's as far as I can go. Five root 7 I will leave as is. The square root of 63 is 7 times 9, the 9 being the important part there because that's a perfect square. Plus 2 times, and 28 is 4 times 7. And I have 4 in there being a perfect square. So this becomes 5 root 7 minus 3 root 7 plus 2 times 2, so that's plus 4 root 7. And so now I've got 5 plus 4 is 9 minus 3 is 6. So that becomes 6 root 7. And look, to finish off today, now that we've got surds in our vocabulary, we can write sometimes our factorisations here with difference of 2 squares. You can say x squared minus 2 is x squared minus the square root of 2 squared, so x minus root 2, x plus root 2. And likewise with the second one. 5a squared minus 7, you could write as a root 5 all squared minus the square root of 7 all squared. So you have a root 5 minus root 7 times a root 5 plus the square root of 7. They're not very simple, but it does allow us to actually factorise some expressions.